Okay, so let's keep moving on, all right? So the specification of orbitals, okay? So N is our principal quantum number, and that determines the energy of an electron in a bound state, okay? So electrons exist in orbitals with quantum numbers L and ML, and those specify the angular momentum of the electron-proton pair, okay? An electron in an orbital with quantum number L has angular momentum magnitude, right? Total magnitude root L times L plus 1 h bar, where we know L can be 0, 1, 2, all the way to n minus 1. Also, an electron in an orbital with quantum number ML has z component angular momentum ml h bar, where now ml takes on all values 0 to plus or minus L. Okay. Additionally, electrons possess intrinsic angular momentum from their spin. Okay, right? So electrons are spinning round and round while they're orbiting the nucleus, much like our sun, moon, planet Earth system. Okay, right? MS h bar on the z component and total magnitude root s times s plus 1 h bar. And overall, we need NL, ML, and MS to specify a complete bound state. And when we're using this term bound state, we're really referring to an electron within an orbital. Our classic view of chemistry, right? Not even of physical chemistry, just chemistry in general, right? Our electron in an orbital is a bound state described by N, L, ML, and MS. Okay, very cool. So let's move on. So now let's look at the energy solutions, okay? So and this is just the solution to the radial component, which is all we need to solve the energy solution, because you can see it's only dependent upon n. And what's important to note, it goes as 1 over n squared. Okay, so for example, if I look at, this is n equals 1 right here. Okay, then we view that, right, here's the negative sign, right? Remember, E sub n is less than 0 for all bound states. And there we've got that negative sign, okay? So if I keep going with this and kind of make connection to the Rydberg equation, right? Here we can see that so I'm going to start over here on this side, okay? Rydberg's constant for any nucleus. So this is what this means. This is Rydberg for any type of atom, okay? We get this constant. It's a collection of all of these constants that you see in this energy solution, right? E to the 4th power, the epsilon squared. There is this, h bar squared and h, and I'll describe why those are just slightly different, why we've got the product h and c. I'll describe that momentarily, okay? So now the Rydberg constant for hydrogen, right? Rydberg for hydrogen comes by ratioing the reduced mass for hydrogen versus the mass of an electron, which they're very close. So RH is very, very close to this R infinity because the reduced mass of hydrogen is just basically equal to the mass of an electron, right? Our reduced mass of hydrogen is Me times MP divided by Me plus MP, okay? And so now what we have right here is, this is RH in terms of joules, okay? And if I multiply it by HC, then I'm going to get my solution in wave number. Okay, so just taking that joule, which if we work through all those constants, right? And so that's actually more directly comparable to the energy solution, right? There's mu e to the fourth power divided by 32 pi squared epsilon squared h bar squared. And the n has been taken out because, remember, my Rydberg can be described by saying 1 over n squared, right? Multiplying this result by hc is what gives it the wave number unit. And so this r infinity, the hc was divided out by the other side. And so that's why the pi gets eliminated, and that's why it becomes h cubed over c, or h cubed times c, okay? I don't want to dwell on that too much longer, just to point out that this Rydberg equation that we talked about at the very beginning, where I made a point that our goal is to be able to predict this thing, well, here we have it, okay? We've done it. So now, the way that we could view this, because we have, this RH is a collection of all these constants, and of course this HC, like I said, it's just going to give the solution wave number, right? We could drop the HC if we wanted the solution in joules. So now what you can see, because it's n squared, when we get n is equal to 2, this reduces the energy by a factor of 4. And when we have n is equal to 3, this reduces the energy by a factor of 3. And when I mean it reduces the energy, what I'm really referring to is it reduces it from the 0 level. And so what that means now, I should really be drawing these as up or down. And so what that means now is as we get up higher and higher in levels, we get closer and closer to this continuum of infinity. And so this is why we use this R infinity, because this whole giant arrow that I just drew is roughly equal to R infinity. Technically it's RH, but again, we know RH is equal to R infinity. And that's because that describes when n approaches infinity, then our hydrogen atom becomes ionized, okay? So this shows us the depth, the full depth of our bound state. So this is very cool. So we can calculate the ionization energy of hydrogen. It's the Rydberg constant. But also when we reduce, that by the 1 over n squared, we get all of these different energy levels, okay? And as you all hopefully remember from Gen Chem, right? When we calculate this delta E, that's going to give me the energy between each successive level, right? Which describes the type of light that we might get as this electron moves up and down through the levels. Okay, so to come full circle, I'm going to go all the way back to my first slide here, right? So those Balmer lines are given by transitions amongst the n is equal to 3 and 4 and 2, okay? These Lyman lines are typically given from n is equal to 2 down to n is equal to 1, and some are some are 3 to 1 and some are even 4 to 1. But what's important is the Lyman describes everything going all the way down to n is equal to 1. The Balmer describes everything going down to n is equal to 2. And the Paschen line describes everything going down to n is equal to 3. Okay? And the bracket line shows everything going down to 4, but we don't have that on the diagram. So that's awesome. So we did it. And what's kind of amazing, what's really cool about this is if we were to compare the energies we calculate from this Rydberg equation to what you actually see in a spectra, it is amazingly accurate, crazy accurate. And it works really, really well for hydrogen and only hydrogen. And we're going to start to see why this immediately fails when we try to describe the same model with helium. It fails. We can no longer do it. Okay.